Okay, in this video what I'm going to do is I'm going to start doing, this is mostly a video for my internet class. I'm going to talk about the 8.1 sequences, but before I do that, I want to talk about a problem from 7.5 that involved finding the surface area when you rotate this function around the x-axis. But the big thing on this problem is that the interval that you're looking at is infinite. So I'm going to do an example here. We have a function e to the negative 4x on the interval x bigger than or equal to 0. So here's the graph of e to the negative 4x, and it goes out forever. We want to take that, we want to wrap it around the x-axis and find the surface area. When we wrap it around the x-axis, we get this thing that looks like a funnel, but it gets smaller and smaller and smaller, but it goes forever. It's kind of an interesting idea. It's very similar to a problem, a classic problem in mathematics called Gabriel's paradox. You can Google it if you want to look it up. It's a very similar looking graph. Has some interesting properties. But we're going to look at this one. And so what we need to find the surface area is the formula. Formula says that we're going to go 2 pi times the integral from a to b. So a to b is our interval of the function, which here is this, times, this is the arc length piece, 1 plus the derivative of the function squared dx. So replacing everything, I'm going to go from 0 to infinity, because that's my interval. And because of that, this turns into an improper integral, which means we'll have to use the techniques from an earlier section in order to figure this out. We'll have to do a limit at the end, okay? Then we have f of x, 1 plus. Now the derivative of f, I did it over here. Here's the derivative of our original function. We're going to take that and we're going to square it. So I have to figure out an antiderivative of this. I noticed that the outside here looks like the derivative of this piece right here. So I do a quick u substitution. I let u be this piece in here. The derivative of that is this. I'm off by 16. You can see I don't have a 16 here, so I scale both sides by 16. And so I can replace e to the negative 4x dx, which is this piece and this piece. I replace that with 1/16 du, and that's right here, 1/16 du. And then the rest of it, 1 plus, this was u, so 1 plus u squared. Then I go to my book and I look at my formula sheets. Formula number 21 allows me to deal with this right here. So from here to here, I've taken the antiderivative using formula 21. And I've also put these two together to get pi over 8. And so I was kind of out of space, so I'm going to continue this problem now. I'm going to replace now all my u's in this answer with this, and then I'll take care of the 0 to infinity. So I'm at pi over 8, and then I have u, which is negative 4 e to the negative 4x over 2, square root of 1 plus negative 4 e to the negative 4x, that quantity squared, and then plus 1/2 natural log of u, which was negative 4e to negative 4x, plus the square root of 1 plus negative 4e to the negative 4x squared, and that's that. And then I close my brackets. All right. Now, what I need to do is evaluate this. Remember, our original integral was 0 to infinity. So I'm kind of out of room, but over here on the side, I've got that bar that I put here. I go 0 to infinity. And that means when we plug in infinity, can't really do that. What we do is we plug t in for all of these x's, and we let t go to infinity. So let me just look at this. There's one particular part in here that appears many times, right? Here it is, here it is, here it is, and here it is, right here. So what would happen if I take that, e to the negative 4x, I replace x with t, and then I let t go to infinity. Well, this is equal to 1 over e to the 4t. And if I let t get infinitely big here, this bottom gets big, the exponent gets big, e to infinity gets huge, this whole thing goes to 0. So anywhere, when I'm plugging in infinity, what's happening is everywhere I see an e to the negative 4x, it's really going to turn into a 0. So let's see how that changes things here. Okay. So plugging in infinity, this piece right here goes to 0, 0 over 2. That 0 should kill all this off. So this is all dead. And then if I plug in, go infinity here, that goes to 0. And then notice here, this is kind of interesting. This is addition, right? So we have to be careful. Over here it was multiplication. If this right here goes to 0, 0 times negative 4 is 0, 0 squared is 0, plus 1, this is just 1. Square root of 1, this was all 0. So this whole thing inside here becomes a 1. Natural log of 1 is 0. So it turns out that when we plug infinity in, or let t go to infinity, the whole thing goes away. It's just 0. So I have equals 0 minus, now I'm going to have my pi over 8. Now let's plug in 0 for x. So e to the negative 4 times 0 is e to the 0, which is 1. So that means all those blue pieces are going to turn into 1s. So let's see what we get. This is a 1 times negative 4 over 2, that's negative 2. Square root, 1 plus, that's a 1. 1 times negative 4 is negative 4 squared, 16, 16. Let me do that, 16 plus 1, root 17. And then we have, let's see, that's going to be a 1, negative 4, so plus 1/2 natural log, negative 4. And then this right here, go through it again, is plus root 17. Close it off. So now what I'll do is I'll distribute this through. So we get positive pi over 4 root 17. And then here to here we get negative pi over 16 natural log of negative 4 plus root 17. All right, I'm going to just double check that on my computer to make sure that that is the correct answer. Yep, okay. So that's correct. All right, so I hope, it turns out, by the way, to be about 3.649. 3.65. So if you had this infinite funnel and you were to look for the surface area, it would actually be finite, which is kind of interesting. Okay, let me now move on to Chapter 8, Section 1. I've got about 40 minutes here. Let me see how much I can get done. So I'm working again for my internet class just right out of the homework set. And I'm just going to pick some interesting ones here. How about 2? This will go quick. 2, they define a sub 1 to be 6. They define a sub n plus 1 to be 5a sub n minus 5. So this is what we call a recursive formula. They give you, for this sequence, they give you the first one, 6, the first number in the ordered list of numbers. And then every other number in this list can come from this formula. So if I want to know what a sub 2 is, then I'm imagining I'm using this formula right here. that the n plus 1 is 2. That means I'll have 5 a sub n, here this will be a sub 1, and then minus 5. So it's saying that the second number in the sequence is actually 5 times the first number minus 5. So this one is the nth number, and this is the n plus 1 number. So I know already what a sub 1 is. A sub 1 was defined to be 6. So 30 minus 5, 25. So the second number is 25. And then to get the third number, I'm going to do 5 times the second number minus 5. So again, to find the next number, I'm going to use the previous one. So a sub 3 should be 5 times 25 minus 5. So 25 was the previous number. 5 times 25 is 125, minus 5 is 120. So the next number should be 120. And then I continue this. If I wanted the fourth number, I'm going to do 5 times the third number minus 5. So it would be 5 times 120 minus 5. And you can keep doing this. All right. I don't think these Formula 1s are really worth me going through because I'm going to do those in class in my lecture videos. So I want to see if you get those. Number 5, I'll just point out real quick, they defined your sequence to be 1 minus 0.5 to the n, and they want to know, does it converge or diverge? And so, hey, what's up? Yeah, it's okay. No? Do y'all need to come in here for something? Yeah, come on in.
Okay.
Come on in.
Well, I don't want to be on your film, okay?
You have to come through here.
You want a water? Play the dumb nasty.
Yeah. So what do you think of this?
You want a water? You want a water?
No, thank you. I'm good.
We drink water here. Let's try. Okay.
All right, so on this one, all we're going to do is just realize that this right here looks like r to the n. And we know that if the absolute value of r is less than 1, then r to the n goes to 0. In other words, if you let n get bigger and bigger, this number gets smaller and smaller. So, I mean, it's pretty obvious. If you take 0.5 and you square it, it gets smaller. Cube it gets even smaller. Fourth degree gets even smaller. So what's happening is this whole thing right here, as n goes to infinity, that goes to 0. So that means that a sub n is headed towards something that's going to 1 minus 0, which means it's headed towards 1. So it actually converges to 1. All right, the next one, 6, I think that's also pretty self-explanatory. 7, let me look at 7. 7 gives you a sub n equals 4 to the n plus 1 over 9 to the n. So if we're trying to figure out if this converges or diverges, you let n go to infinity, the top gets huge, the bottom gets huge. And so you might be thinking like some sort of L'Hopital's rule or something, but I'm just going to do something a little easier. I'm going to split this into 2 fractions. And that really equals 4/9 to the n plus 1/9 to the n. This is kind of an interesting thing that we'll do a lot in this chapter. 4 to the n over 9 to the n, since they're both to the n, I can rewrite it as 4/9 to the n. Because if I want to go from here to here, you know, I just do the n on each one, top and bottom. So I'm just going reverse. Here, same thing. We could have written that 1 as 1 to the n, because 1 to any power is still 1. So by using that fact, we can go back to this. And notice that this number is less than 1, and this number here is less than 1. And then using what I just did a second ago when we had this, we said that went to 0 as n gets big. Same thing here. This number in here is smaller than 1, so it's going to go to 0 as n gets big. This is going to go to 0 as n gets big. So The answer here is that this converges to 0. Okay, number 8 involves the square root. And the only thing I'm going to show you on 8 is just how to maybe start off. I give you square root n plus 2 over 36n plus 2. So we want to know what the limit is as n goes to infinity of a sub n, which is the limit as n goes to infinity of the square root of n plus 2 over 36n plus 2. Now, this is equal to this. So using the limit laws, you are allowed to move that limit inside the root. And that's all I want to show you. Because if you can move the limit inside the root, then all you have to do is the limit of this, and that's like number 6. So, all right, what else? Number 9. 9's interesting. 9 says you've got a sub n equals negative 1 to the n over 6 root n. And this one is an alternating sequence because of the negative 1 to the n. So like a sub 1 would be equal to negative 1 to the 1, which is negative 1, over square root of 1, which is 1, you get negative 1/6. But a sub 2 would be, let's see, positive, right? Negative 1 squared is positive 1 over 6 root 2, whatever that is. Then your next one would be a negative, and the next one would be positive, and so on and so forth. So we're trying to figure out if this goes and it converges to something. So what I'm going to do is look at a theorem that we did in class. The theorem says that if the absolute value of a sub n goes to 0, then a sub n goes to 0. So I'm going to take the absolute value of a sub n. The absolute value of a sub n is the absolute value of negative 1 to the n over 6 root n. And when we take the absolute value on top, it doesn't matter that it's negative 1. It could be negative 1 to any power. No matter what power I use here, I'm going to get either a 1 or a negative 1 up here. And when I take the absolute value of it, it's always going to be equal to. So I'm saying this is equal to 1 over the absolute value of this. Now again, if n is positive, which we're assuming it is, then square root of a positive number is positive. 6 times a positive number is still positive. So I really don't even need the absolute value anymore. Okay, the absolute value kills off the alternating part. So the question is, what's the limit as n goes to infinity of this? So the limit as n goes to infinity of the absolute value of a sub n equals the limit as n goes to infinity of 1 over 6 root n. And that's pretty obvious. As n gets big, this whole thing squashes down to 0. So it's 0. And because of the theorem, I can say, therefore, 3 dots means therefore a sub n must go to 0. Or in other words, negative 1 to the n over 6 root n goes to 0. That's using that theorem. So that theorem is really helpful because it allows us to get rid of that alternating part. All right, next one. A sub n is cosine n over 4. And so what happens as n goes to infinity? Well, what does cosine function do? That's basically a cosine function. Cosine goes like this, right? And since this is a sequence, we're only looking at certain points on that cosine. I don't know where they are. They're all over the place. And as n goes to infinity, those dots are not going to any particular place. You know, they're oscillating. They're hopping around all over the place. So you can't say it's going to 1. You can't say it's going to 0 or negative 1 because it keeps on jumping around. So this limit doesn't exist. We would say that that sequence diverges. All right, I like number 10, or sorry, number 11. So they give you an alternate notation for this. This still means we have a sequence. All right, so they could have written this and it would be exactly the same thing. All right, so what's happening is n gets big. This thing gets big, big number factorial is huge, big number factorial is huge, so we have like an infinity over infinity. We can't use L'Hopital's rule here. We can't switch this into a function of x and use L'Hopital's rule, so we have to do something else. And so what I'm going to do is use the properties of the factorials. So remember that I could rewrite this as 8n minus 1 factorial. And since the bottom factorial is bigger than this one, right? 8n plus 1 is bigger than 8n minus 1. I'm going to start peeling parts off this factorial. So the bottom factorial is 8n plus 1 times 8n plus 1, take 1 away. That's what the factorial does every step. And then the next one is 8n minus 1. And then the next one would be 8n minus 2, 8n minus 3, 8n minus 4, all the way down to 1. So this remaining piece all the way down, I could write as factorial. Notice that factorial is attached only to this one. So this factorial means the rest down. And notice that that is exactly that. So that's what I did. I noticed the bottom was bigger, so I peeled a few off. I cancel these out now. And so really this is just 1 over 8n plus 1 times 8n, and it's obvious from that that as n goes to infinity, the bottom blows up and this whole thing goes to 0. So the answer would be that it converges to 0. I'm just blowing through these quick because I'm just trying to help you out here. I think 12 is doable. 13 we can use the squeeze theorem on. I'm going to show you what tips you off to that. So on 13, a sub n is cosine squared n over 3 to the n. So as n gets bigger, we already said cosine oscillates and it doesn't go anywhere. So you might think, okay, this one doesn't exist, but the bottom is going to infinity. So maybe that somehow counteracts this one's crazy up and down behavior. Well, that's exactly what happens. So I'm going to point out to you, remember that cosine is a bounded function. Cosine is always between -1 and 1. The fact that you square it means that it's always between 0 and 1, right? You square anything, it can't be negative. So what I want to write down is this. Cosine squared n is less than or equal to 1 or greater than or equal to 0. You just have to agree with me on that and believe that that's true just by the definition of what cosine has to be between. And then what I'm going to do is I'm going to divide everything by 3 to the n. 3 to the n. 3 to the n. So this inequality holds true, right? If the original inequality was true, then if I divide everything by the same thing, it should hold true, as long as this is a positive number. 3 to the n is positive. So if it were negative number down here, it would flip the inequalities over. But now let's let n go to infinity. If you let n go to infinity, well, 0 over anything is 0. N goes to infinity here. That's kind of what we're trying to figure out, like what happens here as n goes to infinity. Well, that has to be less than or equal to whatever happens to this when n goes to infinity. But that's obvious. 1 over a huge number is going to go to 0. So what we've done is we've squeezed the part that we're trying to figure out between two numbers. Those two numbers are going to the same place, 0. And so we squeeze our answer right in between 0 and 0. So the only place that this could possibly go is 0. Ooh, 14 is really nice. I think I'll help you get started, but I don't want to give it away. For 14, you're asked to find what this sequence is doing. N over 3 sine 3 over n. So as n goes to infinity, this gets huge, it becomes infinite times, and then 3 over big number becomes small, it's 0, sine of 0, 0. So you get 0 times infinity. That's an indeterminate form. That's a bad situation. So here's my hint. This is a Cal 1 issue. First, we're going to look at this as a function of x. So we're going to switch this over to a function of x. That way we can bring L'Hopital's rule in. Remember, you can't work with L'Hopital's rule on a sequence, because for the L'Hopital's rule to work, you have to have a derivative. For the derivative, you're going to have continuity. We don't have that with this. I talk about it in class. So we still get infinity times 0 here, but watch, we're going to take this, we're going to rewrite x over 3 as 3 over x on the bottom, which is the same thing. If I flip that back up here, I get the same thing. But watch what happens now. As x goes to infinity, this goes to 0, sine of 0, 0. So the top's headed to 0. The bottom, 3 over infinity, is going to go to 0, so the bottom's headed to 0. Now you can use L'Hopital's rule. I won't do it. I'll let you do it. It is going to converge, though. Next one, a sub n, this is 15. A sub n is 1 plus 7 over n. How's my audio going here? It's good, okay. To the n. So what happens is n goes to infinity. This goes to 0. The inside's turning into a 1, but it's always just a little bit bigger than 1, so I'll put a little plus here. This is always a number that's just a little bit bigger than 1, but I'm raising it to a number that's becoming infinite. And again, in Cal 1, this is an indeterminate form. You have to figure out what happens here. The base wants to turn into 1, but raising something to a huge power should make it bigger, especially if this number is bigger than 1. It should try and rip it apart and make it huge. All right, so what we'll do is, again, we're going to have to bring in L'Hopital's rule. So I'm going to define this. I'm going to call it y equals a function of x, which was 1 plus 7 over x to the x. And then to use L'Hopital's rule on this, you actually have to take natural log of both sides. And you do that, you can pull the x out and then go to town with it. If you want, look in my YouTube playlist for my Cal 1 videos this semester on L'Hopital's rule, which is section 2. I don't remember if I put the title. In the videos on YouTube, I don't know if I put the title of those sections. I think it's 2.7. No. Where's... Oh, it's 3.7. So if you're having trouble with L'Hopital's rule, go watch my, my videos for Cal 1 on 3.7, L'Hopital's rule. The heck is that? That was interesting. I'm going to let you think about 16 and 17, because that's the whole point of those problems, just for you to try and figure out what's going on. 18 is really kind of weird. So let's take this one. 18. What is that? I downloaded this new app and it's making this weird noise now on my phone. I better see if I can turn that off. I think I want to uninstall that. Y'all just bear with me for a moment while I uninstall this app. Think about this though. What's happening as n goes to infinity? All right. I'll see if that helps. Hey, come on in, man. I'm almost done. Yeah, I've got about another 2 or 3 minutes, I think, on this. Maybe a little more, 5. So as n goes to infinity, this thing right here just keeps oscillating back. So like, if n is 1, I get -2. N is 2, I get 4, then -8, then 16, then -32. So the top is doing this. The bottom is getting huge, and it's becoming infinite. So you could say that the top is headed to infinity, the bottom is headed to infinity. The thing is that the top is switching back and forth between positive and negative big numbers. So this is really kind of like a what the heck is going on. So what I'll do is first let me see if that theorem that we had will work. That absolute value problem. If I take the absolute value, right, take the absolute value of this, I need for it to go to 0 for this theorem to work. So let me see, the absolute value of the top is just going to be 2 to the n. So that's just going to, it's going to wipe out the alternating part, and then I'll have on the bottom 6n factorial. And then what I need to do is figure out what's happening here. Well, 2 to the n, let me just write down what 2 to the n would mean. It would be 2 times 2 times 2, and then I would have all the way, I would have actually n of those. And then on the bottom, I have a 6 out here, times n factorial would be n times n minus 1 times n minus 2, and then all the way down to 1. And so if I look at it this way, then how many of these things in parentheses will I have? So look at it this way. If I had, let's say, 5 factorial, I would have 5 times 5 minus 1 times 5 minus 2 times 5 minus 3 times 5 minus 4 would get me down to 1. So if I have 5 factorial, I have 1, 2, 3, 4, 5 of these, and that last one is 1. So notice that I would have n dot 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 all the way down to 1. So I would have a total of n of these factors. So these actually line up like this exactly. So we know the last one out here, the last one, no matter what n is, right? So like if I fix n, I know that the last one is 2. The one before it has to be 2, and this has to be 2, right? So we get 1. And then what happens to each of these other ones? Which is bigger here? This right here, 2 over n, is going to be, let me see if I can write this another way. I think it'll be easier if I swap it up. Let me rearrange things. Okay, I'm going to flip the whole thing over. So I'm going to put the 2 over 1 in the front, and then the 2 over 2, which is 1, times, and then at the back I've got 2 over n minus 2, and then 2 over n minus 1, 2 over n. So I'm looking at each of these here. Darn it, I went a little too far. Let me move my camera so I don't have to erase that, because this is the last problem I'm going to probably do. So these are a bunch of dots in here. Okay, so what I'm going to do is I'm going to show that this has to be stuck between two things. Oh, and I had the 1/6 out there. Okay, so what's happening here? All of this multiplied together has to be greater or equal to 0 for sure. And then over here, I want to try and get it smaller than something. And how about 1/3? How about 2 over n? So let's see if you agree with this. I'm not even going to mess with this right now, okay? But do you agree that that number has to be smaller than 1? Well, if n gets big, this number is going to be smaller than 1. This number is going to be smaller than 1. This next number is going to be smaller than 1. All the way until I get down here to this one, which is 1. And then I have over here these two together, which would be like 1/3. So all of these multiplied these here should be like 1/3, smaller than 1/3, and then this times 2 over n here. So all of this has to be smaller than, if all of that multiplied together is 1/3 times 2 over n, then that's definitely smaller than 2 over n. Hopefully you follow that logic. So for large n, as n gets bigger, these are all going to be true. These are all less than 1. And then now I use the squeeze theorem. I let n go to infinity, and this goes to 0, and then this side over here already is 0. So that means that middle sum must go to 0. So that means that the absolute value of the sequence goes to 0, which implies that the sequence itself goes to 0. And so it converged. All right. The monotonic part, increasing, decreasing, I will do examples of that in class, so you should be okay with those. I hope that that helps.